Good morning. Today's lecture is about one aspect of the diffusion model, and it's something which is related to the structure that you have in the data. So when you generate data, so in particular in image, but you can think also to sound and videos, so data has structure, has microscopic structure on the microscopic scale, has structure on the macroscopic scale, has features. And what we would, in natural question is, when you generate along the backward Langevin dynamics, how all this structure emerge? And the first question, maybe it's this one. So imagine that I train a diffusion model on images of cats and dogs. And so this means that when I start the diffusion process, I start from white noise. Then I have the Langevin trajectory during the backward process. So how actually the Langevin trajectory decide, quote unquote, at a certain point, to give you a dog or to give you a cat? So is this correspond to a kind of transition? And the answer is yes. You will see it's a kind of dynamical, actually, phase transition. And I want to discuss using a simple model, and then I will tell you what other models have been studied and how much studying simple model is relevant for real system, to study really how the structure emerge and whether the large-scale structure emerge first or emerge later during the backward process. And this actually, at the end, I mean, it's also interesting because then actually you can maybe use this idea to study the structure in the data, which is a very important problem actually in machine learning in general. All right, so we'll start with just start with the slide, but now I go back to the board, and then for the final part, I will go back to the slide. All right, is the question clear? Okay. So now I have to switch on the light. Éclairage tableau. Okay. All right, so what I want to do is, like usual, in physics, in theoretical physics, just to study a simple model. Of course, this is not, so I would say the one important ingredient that we are going to put, and which I think is an interesting ingredient in general in all this business, is that it's natural to consider probability distribution that you want to generate, which are in very high dimension. As I told you yesterday, it's the high dimension which makes the problem challenging. I mean, sampling from data, sampling new data, if you are in dimension 1, it's not a big deal. Same thing in dimension 2 and dimension 3. When you are in dimension 1000, then the problem is challenging. And also, I mean, the fact of considering high dimension, it's something that, as you know, as statistical physicists or mathematicians, sometimes there are some simplification that emerges. So probability law in 1000 variable, sometimes actually it's more simple than the probability law in 17 variables, which I think is 17. You use 17? Okay. It's a quote from Gerard. I even remember the 17. Okay, well, as physicists, well, you know, I mean, we study microscopic objects. We can study microscopic objects, even though there is a statistical description at the microscopic level, because there are some emergent phenomena. And so, well, you will see that studying the high dimension probability distribution, it's important. So what I'm going to do is to study a simple model to study the problem that I gave to you. So the simple model of data, of let's say high dimensional data, with two classes. So what I want the two classes correspond, quote unquote, to the cat and the dog that I described before. Okay, so what are the ingredients that I'm going to put? So, okay, so first, I mean, in computer science, I mean, if you are in physics, if you want to do a very simple model of, for example, a phase transition, in general, when you teach a class, you go to the Curie-Weiss model, which is the ferromagnetic model with all spins coupled together. So in computer science, the equivalent of the Curie-Weiss model is Gaussian mixture. So we are going to consider is Gaussian mixture. And the Gaussian mixture that we are going to in high dimension, so in dimension D. And so what it means is that now the vector x comes from a probability distribution, and this probability distribution we are going to choose in this way. So when I draw x, with probability 1/2, I'm going to draw it from a Gaussian, which is centering mu and a certain covariance sigma. And with probability 1/2, instead, I will sample from a Gaussian with centering minus mu with a covariance sigma. Okay? Now, mu and minus mu, well, mu, just to be simple, the simplest case is let me take it 1, 1, 1. Okay? So let's say that the cut corresponds to plus mu, and the dot corresponds to minus mu. Okay? So it's Gaussian mixture, and so it's very high probability. These are, let's say, the probability distribution is concentrated in two different places, non-overlapping places. And now for sigma, we can actually do something that, so for sigma, I'm going to consider that sigma has eigenvalues. So let's say it's, we study eigenvalues. And the eigenvalues of sigmas, if I plot, let's say, rho of lambda, I'm not going to give a particular functional law, but let's say that I take something which goes like this, okay? Why I'm doing this? So what I want to describe is that there are some very large eigenvalue and very small eigenvalues. And why I'm doing this is because, as I told you, in real images, and actually many problems actually in data science. So in real images, if you look to the what is called the power spectrum or the Fourier component or the covariance matrix of the data, what you have as a function of k, you get something which is actually close to 1 over k squared. Okay? So the covariance matrix of the data of real images in Fourier has this kind of behavior. So you have at small k very big amplitude, and large k small amplitude. It looks like a little bit like a critical system in physics. Okay? So I'm going to describe this in this kind of way. So I mean, I have a distribution of lambda. And then I do another hypothesis just to simplify my life, is that mu is let's say, parallel to one of the eigenvector. Of sigma. Okay? So with a certain value, so let's call it lambda 1. So this will have the eigenvector which corresponds to direction mu will have an eigenvalue lambda 1, just to be simple. Okay, so that's the model. And so
1/2, 1/2.
Sorry?
And the mixture is...
It's 1/2, 1/2. Yes, exactly. So you can, and I will tell you something, you can also play putting different fractions to see how the model, and when the model, actually the diffusion model, is able to recover the correct fraction, and we'll discuss this at the end. For the moment, it's 1/2, 1/2. So the idea is the following. Probability law is concentrated around two different regions, and we want to understand actually how the system, which starts from white noise, will decide to go toward one probability law or toward one Gaussian or the other Gaussian, which correspond to the cat and the dog. OK, so now this problem is simple enough that we can solve it exactly. And it's really probably the simplest case that one can consider. And so let's study it in great detail, and then I will tell you all the generalization that one can do. OK, so first thing is, what is the probability? So if I take the same notation of yesterday, P0 of x, well, P0 of x is with 1/2, you have these probabilities, this Gaussian. So it's going to be minus x minus mu, sigma minus 1, x minus mu, divided by 2, divided by square root of 2 pi to the d, and then you have the determinant of sigma. And then with probability 1/2, you have the other Gaussian, minus x plus mu, sigma minus 1, x plus mu, divided by 2, and then the same normalization factor. OK, so now we want to understand, first thing, so my aim now is really to study the backward dynamics, understanding what this Langevin backward dynamics is doing. So in order to do this, to study, I have to get the score. So in this case, we are playing a game in the sense that normally you don't have the law. You don't know the law, you just know the data. So in this case, we are playing, let's say, God's game. So we know P0 of x, and we really want to study what this dynamics is if we were able to learn the score perfectly. So what is the score? So we want to get Pt of x. And so I remind you that x at time t is equal to x0 exponential minus t plus square root of 1 minus exponential minus 2t times g, where g is a Gaussian, which is n 0, 1. Okay. So, okay, if x at time t, let me call it x at time t is like this, what is the distribution of x of t? Well, let's just read it from above. So if I draw 1x of t, well, with probability 1/2, I will get a Gaussian which is, so let me say it, with probability 1/2. What do I get? I get something which is centering mu, exponential minus t, plus exponential minus t times a Gaussian variable. Let's call it a g tilde, plus square root of 1 minus 2t with this Gaussian variable g of t. Okay, I think it's okay. And this g tilde is distributed with a covariance sigma. Okay, and now with probability 1/2, I have minus mu, exponential minus t, then plus exponential minus t times g tilde, again with the covariance sigma, plus square root of 1 minus exponential minus 2t g of t. And now, well, let's go in the basis that diagonalize sigma, just to get things simple. So maybe actually I can. Okay, so let's say I have the first component, I equal 1. This one is the one that corresponds to the direction mu. So in the direction mu, well, what do I have if I project on the direction mu? What I have is that x1 will be with probability 1/2 if I project. So it's going to be square root of d exponential minus t plus exponential minus t. And then I have, let's say, a Gaussian variable with, let me write, of square root of lambda 1, which let me call it g bar, plus square root of 1 minus exponential minus 2 t g bar bar bar, where g bar and g bar bar are both n 0, 1. Okay. And then with probability minus, with probability 1/2, I have minus square root of d exponential minus t. Okay, I'm coming. Yeah, so it's coming from the fact that the, okay, let me do it here. So I have, mu is equal to 1, 1, 1. So I'm projecting on the unit vector. Now, you could ask, okay, here I'm doing a choice, which is the fact that the two Gaussian are very well separated, because mu, the norm of mu, is square root of d. So it means that I have two Gaussian very well separated, or the square root of d, and then they have fluctuation in all directions, which are of order 1. This, I think, it's a good case because, again, when I give you an image of a cat or a dog, you don't have to, you don't have doubt in general. It's either a cat or it's either a dog, which means that you can retrieve with probability 1, you can know with probability 1 whether it's one class or in the other. If instead I had two Gaussian with overlap, it would mean that sometimes you don't know whether it's one or the other. So this is why we take very different, very non-overlapping Gaussian. Okay, this is for x1. And then I have x, so let me, and for I different from 1, well, it's simple. I have xi. Now, well, if I project on a direction which is orthogonal to mu, this goes away. And so I just have this term. So this is going to be just exponential minus t square root of lambda I of g bar plus 1 minus 2t of g bar bar. Okay. All right, so let's now write what is pt of x, and then we get the score. So now pt of x is trivially, so pt of x, we can write it as the product over I different from 1 of pt of x I, and then we have p1 t of x1, because, these variables are independent, as you see. And then, So what we have is that p t I of xi, we can just read it from here, is exponential of minus xi squared divided by 2 gamma it divided by square root of 2 pi gamma it, where gamma it, well, here you have a sum over 2 Gaussian variables which are independent, so the variance is exponential of minus 2t lambda I plus 1 minus exponential minus 2t. All right, and then what is P1? Well, P1 of t x1, this is 1/2 of exponential of minus x1 minus square root, sorry, minus square root of the exponential minus t square divided by 2 gamma 1t square root of 2 pi gamma 1t plus 1/2 of exponential of minus x1 plus square root of the exponential minus t square 2 gamma 1t square root of 2 pi gamma 1t. Okay, easy. And now, well, if you have pt of x, well, we can get the score, right? Remember the score at time t, st of x. I'm sorry, I'm changing notation. Sometimes I put it here, sometimes I put it here, but it's still the same score. This is equal to the gradient of the log of pt of x. Since we have pt of x, we can just compute it and look at it. Yeah.
Sorry, Giulio, before you had some parameters theta, I guess they're still in.
So here, yeah, I'm playing the game that I've learned the perfect score. I have a perfect machine, I did a perfect optimization, and so I get the score. And what I want to study is, in this case, what the backward dynamics behaves. Then there is the second, there is a third, another problem, which is, okay, what about if I don't learn the perfect score, what's going to happen? This is more, I discuss this more tomorrow. Okay. All right, so let's go. So now, again, well, if I, sorry, here I should have put a vector. So let's look at the difference. So now, remember, the equation, the backward equation is dx d tau, which is equal to x plus twice the score, st of x, plus a noise, eta of tau. So now let's look at component per component. So now we know that, well, the component x1 is different from the other. So let's look at the score for component 1, the score for all the other components, and then we write down what are the backward Langevin equation. Okay, so now, what is S1? Or maybe let me start with Si t of x for I different from 1. Well, let's take it. So what we have to do is the derivative with respect to xi of log of pt of x. Well, look at what is pt of x. So it's independent between the different x. So what we get here, this is just the derivative of xi of log of pt of I xi, which is just equal to, we have it there, it's just equal to minus xi divided by gamma t. Of course, here is everything is super simple. Even in the backward process, actually, the x are not talking to each other. But I will show you. You can just go a little bit. In general, it's not the case. And even if we complicate a little bit the model, it will not be the case. Okay, so this is for I different from 1. And now if I take I equal 1, so S1 of t of x is equal to the derivative with respect to x1. Well, same thing now, since this is a product, so it's going to be just log of p1 of t of x1. And so I take what I have there. So this is the derivative with respect to x1 of log of 1/2 exponential of minus x1 squared divided by 2 minus d exponential minus 2t. Sorry, here there is a gamma 1t. Here there is a 2 gamma 1t. And then I have a plus square root of d exponential minus t x1 gamma 1t. And then I have plus 1/2, same thing, but there is just this sign which is going to change. Minus square root of d exponential minus t x1 gamma 1t. Okay. Okay, now, well, when I take the derivative, you see that all this, I mean, here I can take the 1/2 out, just a constant, so it's not important for the derivative. And then, well, these terms here, they have in common these two terms, so they also take it out. And so what I get is minus x1 divided by gamma 1t. This is the derivative of the log of this term, same thing that I also have here. The derivative of the log of this term is nothing because this is a constant. And then I remain still with a term which is plus the derivative with respect to x1 of log of 1/2 exponential of square root of d exponential minus t x1 divided by gamma 1t plus 1/2 of exponential of minus square root of d exponential minus t x1 gamma 1t, which I can rewrite in a way that I like a little bit more. Well, don't ask me why, but it's log, well, probably because it reminds me of things from the Curie-Weiss model. Square root of d exponential minus t1 x1 gamma 1t. Okay, so now we have the score for all components. Okay, so now questions? Okay, so now let's write the equation, the backward equation for the two components, and let's study them. Maybe I can write it, I can write them here. Okay, so, okay, for component I different from 1, so what I have delta xi d tau equal to xi plus twice, and then let's see what is the score for the case. It's just minus xi gamma I of t plus eta by I of tau. So this is just, so this equation is just psi d tau equal to, well, xi you can write in this way, 1 minus 2 gamma I of t. Remember, t is a function of tau, plus eta I of tau with, so gamma I of t of tau, which is equal, so I wrote it there, is just exponential of minus 2t lambda I plus 1 minus exponential minus 2t. Okay, so this is for I different from 1. And for I equal 1, so this is more, it's a bit more, it's different. So remember, what is x1? x1 is the coordinate which separate the two Gaussian. So it's really the one that is going to tell you whether you go more toward the one or toward the other. And so it's the one that we are able to track in order to understand the formation of classes. So, okay, so now dx1 d tau is equal to x1 plus twice the score, and now the score, we have it there. So there is a term which is minus x1 divided by gamma 1t. And then we have the other term, which is the derivative with respect to x1 of log cosine of square root of d exponential minus t x1 divided by gamma 1 of t plus eta 1 of tau. Okay. Now the nice thing is that in both cases, actually, you can rewrite this as, so this thing here, you can write it as, to have some physical intuition, you can write it like minus the derivative of some effective potential, which depends on time, on the variable xi. Well, and what is this potential is, in this case, just to give you the idea, is just, so would be minus, minus xi squared divided by 2, 1 minus 2, gamma I of t. And here, if you want, since I wrote it this way, well, it's the same thing. So here you can also write this like minus the derivative of v effective 1 with respect to x1. So this is 1 and depends on t. Well, I have too many indices, so this I. This is 1 plus eta 1 of tau. And now the v effective 1 t is equal to same thing than before. So it's minus x1 square divided by 2, 1 minus 2 gamma 1 of t. And then we have the term which is minus log parabolic cosine of square root of d exponential minus t x1 gamma 1 of t. Okay. So now we have reduced the problem to something which we can have a lot of intuition. These are just independent equations in a potential which changes with time. So now we can study how this potential is changing with time and how actually, well, you are going to get the classes to create different classes at different times. All right, so the first thing, now I'm going to study at very beginning of the backward process. So which means t is very large, tau is very small. So and the point, what I want to show is that actually there are different dynamical regimes that appear. There is one regime which is at the very beginning of the backward process, which we're going to call regime 1. And then well, there's a second regime that happens later. And this is, well, it's really sharp when the dimension d go to infinity. OK, so regime 1. So what is regime 1? What is the regime of, so maybe I can let me write here. So here we have, remember there is t, which goes from 0 in principle to infinity, but let's say, and then we have tau, which is moving this way. And now, if you stare at the equation, what do you have? So the equation on here on I different from 1, well, you see that there is a potential which changes with time. There is nothing more. So here, in principle, all the dynamics is taking place on time which are of order 1. Here, you see that there is one, particular variable that you have here. When d go to infinity, well, but time go to infinity, well, there will be a scaling regime in which this thing is going to be of order 1. So what you find here is that this is telling you, in a sense already, there will be a regime of time in which square root of d exponential minus t will be of order 1. And in this regime of time, this is going to be of order 1. Whereas when t is of order 1 and d go to infinity, this go to infinity. So clearly, we have to separate the regime. And so there is a first regime of time, which corresponds to times in which square root of d exponential minus t is of order 1. In order to define it, let's say that I define square root of d exponential minus ts equal to 1. So ts will be called speciation time, for a reason that you will see later. And which means that I have a time here, ts, which goes like which is equal actually to 1/2 log of d. So when d goes to infinity, well, this goes becomes very large slowly because it's a log of d, but it becomes very large. And what we are going to study the dynamics on a regime here, which is a regime of time which is of order 1 around this time ts. So which means actually that in this case, so I'm going to define, so square root of d exponential minus t. So I'm going, sorry, the time t, I'm going to define it as ts plus delta t. And delta t is going to be over 1. That's the regime that I'm going to study. Yeah.
A surprising thing here, this thing does not depend on the eigenvalues. Even lambda 1 has disappeared here. It's
exactly. Exactly. Yeah. So I'm going to come to this.
Sigma is really curved or not?
Not in regime 1, yeah. But then in regime 2, yeah. So it's well, this you are spoiling a little bit my, but it's okay. Yeah. So let's see in regime 1 what the equation are doing. So as Gerard said, so let's look at gamma I of t. So gamma I of t that I wrote now, well, it was somewhere. So it was, I think, lambda I exponential minus 2t plus 1 minus 2t. Well, in this regime, it's just equal to 1 for all I. Okay. So this means that if I look at the equation for I different from 1, which I have there, well, what's going to be? It's going to be dxi d tau equal to, so gamma is equal to 1, and I get minus xi plus eta I of tau. So nothing is happening on I different from 1. So what I have here is that all the xi are just noise. They start as Gaussian noise, and they remain just Gaussian noise. Okay, so this is the vi on this regime of time. Okay, so nothing happens on xi. Now let's see what happens on I different from 1. Sorry, on I equal 1. So I equal 1, so I'm going to get delta x1 d tau, which is equal, well, same thing here. So I'm going to get a term which is minus x1, which come from the sum of these two. And then I have plus twice the derivative with respect to x1 of log of hyperbolic cosine of what? Of square root of d exponential minus t, which is then exponential minus delta t, x1, and then the gamma 1 is equal to 1, so that's it, plus eta 1 of tau. And now exactly as I said here, so in this case, you see this is an Oostland-Uhrenbeck process, so we are coming back. What we are saying is that when we come back here, all the xi are on this time regime, they are doing nothing. They are just, fluctuating in their well. Now what I want to describe is that instead, you see that instead the effective potential on x1 is moving. And let's discuss, you can study the effective potential on x1, how it changes with time. And so I just give you the solution because it's very easy. So let's see how it behaves. Okay. So when delta t is much larger than 1, v1 of x1, okay, what is it? So delta t much larger than 1 means we are around here. So how is the potential? I always ask you about Gaussian, and so you can know. Okay. Well, I'm sure you know. It's delta t go to infinity. This go to 0. So this is equal to 1. You take the log. That's 0. So you just get a potential which is like this. So it behaves exactly. You start from it's just Gaussian, and nothing is happening when you are at the very beginning of the backward process. And now what happens instead when delta t is much less than 0. So now it's becoming, so we are around, still of order 1, but we are around here. Well, if you study, so maybe I should write it, what the potential is. So the potential V1 is equal, we say, to x1 squared minus twice log of exponential minus delta t and x1. Well, if you stare a little bit to this, what you get is a potential which is has this form. So so between these two regimes, when delta t, let's say, it's for, I mean, it's, I don't remember exactly what is the value, but at a certain value, delta t, let's say, of order 1, what you get is that you have the symmetry breaking. So, I mean, the symmetry breaking. You have the, the transition from one well to two well. All right. So what does it mean in terms of trajectory? So the trajectory, if you now think in terms of trajectory, what's happening is that, imagine that, so now I'm drawing, let's say, x1 here, and this will be my backward time. So, so at the beginning, x1, let's say, is distributed as a Gaussian variable. And now when you study trajectory, you have trajectory like this. And then around the time which corresponds to the speciation time, then trajectories start to go to different places. Of course, this is not sharp for the moment. I mean, you can have a trajectory which goes like this, and then it goes up, or a trajectory which goes up, and then it goes down. Okay? All right. However, so this, indeed, so around this time, which is the speciation time, you really have that, I mean, the potential is moving, and what happens is actually this height that you have here, and this one, which you have here, in general, so this, let me check that I don't get it wrong. So this is, should be of order exponential minus delta t, and this one should be of order exponential minus 2 delta t. So what's happening is that this potential is just, so first you have the two wells, then the two wells go farther and farther, and deeper. So which means that when it becomes deeper and deeper, it becomes more and more unlikely actually to do this jump. And when you go out, when you are in the regime, so now you are in this regime here, but then, so this was what we call regime 1. Now what you can think, there will be a regime 2, which are the time scale of order 1. So this is t of order 1/2 of log d plus something of order 1. And here you have time scale, which are of order 1. So in this regime of time scale, while the barrier is of order, actually, I mean, this is of order square root of d, this is of order d, and that's it. I mean, you don't have any possibility that the system will jump from one to the other. Because, yeah, just a moment. The barrier is of order d. The time scale that you have is of order 1/2 of log d. So over this time scale, well, the probability is just 0 to make the jump. Yeah?
Is there a way to get more critical point? I mean, in characterise model, if you perform this kind of thing, I don't know how it is, you get metastable states, so you get a bifurcation for these two extra hours. So maybe maybe some structure could lead to this.
Sorry, the question
maybe some different structure could lead also to this, or are you? Is this the only bifurcation you have in your framework?
In this model, yes, it's the only bifurcation. Then I don't know. I mean, you can do the same, and I will say it. You can play the same game with characterise. So you start from a probability distribution instead of Gaussian mixture, probability distribution of characterise, and it's a more complicated computation, but you get the same thing. So you have the same bifurcation.
Because if you do characterise for some dynamics, general, probably not exactly the same, or put some disorder system, you get a triple point, and you get some metastable states at the size of the well. And this slow down a lot.
No, so let me think. So for the moment, I mean, here I took probability 1/2 and 1/2. So if you, for the two Gaussian, if I take a probability p and 1 minus p, then yeah, they will be slightly different, the wells, in such a way that the trajectory have some bit more probability to go to one side to the other. But no, you don't have metastability, really. OK, so now why this? So this is why it's really a transition. So I mean, when you zoom on time ts, it doesn't look like a transition. But now to see that it really is transition, you can write p. So this is the probability. So let me say this thought experiment that will become a real numerical experiment in a few moments. So imagine that I take a trajectory until a time t. And then, I'm doing the backward process. I run the Langevin equation until a certain time. And at this time, I clone it, which means that I start to use two different thermal noise. So the trajectory is going this way, and then, it bifurcates. And so then, depending on at which time I do it, I have a certain probability that the two trajectory ends up in the same Gaussian or not. So now I write the probability that these two clones end up in the same Gaussian at the end of the backward process. So it's p of the clone as a function of the time t at which I clone along the backward process. Let's say be here. And I divide this by the speciation time. So what you get when you do this is you really see something which goes from, let's say, 1 here. If I clone, I mean, I clone here, I mean, the trajectory I have already separated are well beyond the speciation time, so there is no probability that actually I jump back. So the two clones will end in the same. And if I clone too early, so if I clone here, for example, well, probability is 1/2 that they end up in the same Gaussian. Okay? And this should happen around Ts. Now, this is what you get for a certain dimension d. Now, if you increase the dimension, what you see is something like this. And increase more the dimension is something like this. And then when d go to infinity, you have really a true transition. Okay? And actually, this probability, I mean, I don't have time, and maybe it's not so instructive, but you can compute exactly just using analyzing this stochastic process. Okay, so in regime 1, what you get is that in this regime of time scale, the system is deciding whether to go to one class and to the other, but there is no, I mean, for the moment, there is nothing about the lambda I as a Gerard American. All right, now let's study regime 2. What happens in regime 2? If there are no questions.
Question?
Yeah.
Sorry, so you drew that as being like a discontinuous and large D limit?
Yeah.
Like the potential here is like doing a second order transition, so what was
the thing is, the fact is that you see I renormalize with respect to Ts. So what's happening here is that you have a time scale which is going to infinity, and in this regime of time scale, on time scale of order 1, around this things are happening. So if I renormalize time with respect to Ts, well, the times of order 1 will just shrink to 0. Just the way to see it. Okay. All right, so now let's study regime 2. Okay. Okay, so now in regime 2, well, the equation on dxi, so let's see, the xi for I different from 1 is dxi dt, which is equal to, well, we wrote it before, I think. It was just xi 1 minus 2 gamma I of t plus eta I of tau. And then we have the one for I equal 1, which is dx1, sorry, this was tau, d tau, which is equal to, well, let's see it. So there is this first term here, and now, well, okay, there is the first term, which is the same, x1 of 1 minus 2 gamma 1t. And then, well, let's take the derivative of this. So here we have plus 2. So there is square root of d exponential minus t gamma 1 of t And then here we have the hyperbolic tangent of square root of d exponential minus t x1 divided gamma 1 of t. But, well, gamma 1 of t is of order 1, t is of order 1, d is going to infinity. So this means that, remember the trajectory, what they are doing. So x1 has going on one side or on the other side. And we say that in regime 1, well, once x1 has decided to go to, let's say, the right, the Gaussian on the right, we'll never actually jump to the Gaussian on the left. So the fate is chosen. So if x1 is positive, we remain positive. If x1 is negative, we remain negative. So let's say if x1 is positive, so let's say if x1 has chosen class, let's say, plus 1, which corresponds to plus mu, well, then when I take here d go to infinity, this is positive, this is just equal to 1. And if, so it goes away. If it had chosen class minus 1, well, it'd be equal to minus 1, so it would have a minus. Okay. So now what do we have here? So this is, in this is the backward, is just the backward equation for a single backward equation for a single Gaussian, variable. A single, let's say n0 lambda I. And this one is, same thing, is the backward equation for a single Gaussian variable, which is in plus square root of d, and it's have lambda 1. Okay? So because here, actually, it's what you have. It's true that you have the two potential, but since you are sure that you are on the x1 which are positive, you are just looking at one of them. Okay. So now the only thing that I want to make you notice is that let's look at gamma. So now the question is, which are the variable, the xi, which are reconstructed first? Are the one with the larger lambda or with the small lambda?
Simple.
Why?
Because you have this.
So reconstructed first means here.
Okay. I'm just thinking you have this function with lambda where it's like this, and for large values it's small.
So there is a trick to see without thinking to the computation. Think that you have variable here which have a random with a certain amplitude which is square root of lambda. And now you put noise. So when you put noise, you forget about actually, because you have this variable and then you have the noise, when you are going to forget, the initial variable. If you see that if lambda is very large, so the initial value of the variable is very, very large, the fluctuations are very large, you have to inject a lot of noise actually to destroy it. Which injecting a lot of noise means being here. And see, this you can see just if you remember, it's gamma I of t is lambda I exponential minus t plus 1 minus exponential minus 2t. And so, well, you see that if lambda I is very large, so you will get a Gaussian, you will get, let's say, the crossover takes place. So let's say later in t, which means at the more at the beginning of the backward process. Backward. If lambda I is much larger than 1. And well, you just see it from here or from the simple argument that I gave. So now, if we summarize what we have found is, so the image that we get from this computation is that when we do the backward process, first thing you create, you decide whether you go to one class or the other. Then, actually remember the x1 has to be of order square root of d when it arrives at this Gaussian, or minus square root of d when arrived to this Gaussian. In regime 1, x1 is of order 1. So it means that you have just decided whether you go this way or this way. And then it's in regime 2, actually, that you create all the property of the image. So you decide which kind of images, which class you decide in regime 1, all the property of the image, so all this lambda, for example, all this are created in regime 2. That is the... And now, well, a question, maybe what I said, is, now if I didn't have taken probability 1/2 and 1/2, and I say that I have 1/3, I train the system on 1/3 of dogs, 2/3 of cats. When the system is going to fix whether you get 1/3 or 2/3, again in regime 1. As I told you before, I mean, once you're in regime 2, you never change class. So from this, you see, I mean, it's a simple exercise, but you get a lot of information. So you know that there are different dynamical regimes. There is the first regime in which you fix the fraction of the different classes, and you fix which class you go to. And then actually it's in regime 2 that you really create the image. OK, so now in the rest, what I want to show you is, well, this is a very simple computation. I mean, what can one do? I mean, can one trust the result? But before, I mean, just look at numerics to see whether this works or not. But before saying this I would like to, yes, I'm coming just to a question. I would like to tell you, I mean, what can one do more? Of course, once you have done this computation, you could say, OK, can we do it for other models? And in particular, and since we are statistical physicists, can we do it for statistical physics model, not just mixture of Gaussian with variables which are independent, but can I use ferromagnetic system or other kinds of system? Yeah, of course.
So here again, there's a big role for the separation of these two regimes in the fact that what we discussed already, that is mu has a very large norm.
Yeah.
If the signal you want to find is smaller, then the two regimes would be more
closer. Yes. Yeah, they will be closer, indeed. So yeah, we'll just, I mean, it's the fact that you can really separate. I think this is correct in the sense that if you cannot separate, it means that you cannot recognize which class it is. But you're right, the scaling by square root of d is just chosen in this way. In reality, what you expect is that, I mean, there is a separation of time scale, but the time scale in regime 1 doesn't have to scale with the log of the dimension of the image. Yeah.
Yeah. So we had this story yesterday of this kind of walking bandpass filter in the RG adjacent story where the larger wavelength things were reconstructed before the lower. Is this closely related to that, or we're just making these big decisions before the
So actually, not really. So what happens is that so even without doing this RG scheme, it happens that in images and in generally in many other data, you reconstruct the large scale first. And the reason behind this is that, well, is the fact that the fluctuations are in scale are larger for the larger scale, like in physics. And since you have larger fluctuation on large scale, so when you put the noise, you kill them. You need a lot of noise to kill them. So when you come back, it's the first one that you reconstruct. But it's not by choice of the method. It's not that the method that is being constructed like this. It's that the data are like this, and so well, you reconstruct first. Whereas in the other case, would be really independent of the data. Is just a hardwire in the method. Oh, yeah.
This is kind of a stupid question, but how do you see like the class that you chose for X1 versus
sorry. So here you don't. So in regime 1 you have this trajectory, and so with probability 1/2 you can get a trajectory goes toward one Gaussian and toward the other. So once you are in regime 2, I'm just conditioning. So conditioning on the fact that x1 is there, and I know that it cannot change. Yeah. Okay, so let me tell you what are the other cases in which you can do the computation. And I'm sure there are others, and maybe some of you can do it in other cases. Or maybe I can do it here. Okay, so generalization. So one thing that you may want to do is do the same computation, but not on this simple Gaussian mixture, but on more general, actually, model. And so you can do more general, I would say, computer science model. General CS. And what do I mean by this? Well, you can take, for example, Gaussian mixture with more than 2. And 2. Let's say here we had, so I don't know, you could do, for example, you can mimic some hierarchical structure. So you put Gaussian, which are like this, like if there was one cluster here, and then within the cluster you have, for example, these 2. That's a possibility. Or you can actually take the Gaussian mixture, but they live on a lower dimensional manifold. because, well, many people think, and I think it's right, is that the data, I mean, when you have an image which is L by L, so the dimension of the vector is L squared, but it's the, when you look at the, and so you are in RD, but actually the data don't live really in RD, they live in a subspace which has a lower dimension. So for example, I think for images, the ones that I show you to you, like the cat and the dog, I think it's, the dimension is probably around 20, whereas actually the image, the dimension of the image is much more. Still big, 20, but it's not as big as the dimension of the image. So it's an interesting case. So this has been done. Again, I will send a reference to Thierry, so I will put them. And then there is another one, which is what is called the, well, in this case, the lower dimensional manifold, which is just flat, or you can do it also, well, let's say on manifold which are complicated and curved, and this has been also done to a certain extent. So this lower dimensional manifold, I think it's, so there is one in the group of in Bocconi, Marc Mézard, and then I think there is a paper also by Nicolas Macris at EPFL. So two, now more general, but now not computer science, but statistical physics model. So why, I mean, why doing this? Two reasons. First is that in statistical physics, we have very natural high-dimensional probability law. And this is what we want to study. And we know, well, I don't know, the Ising model in 2 dimension, in 3 dimension gives you the Gibbs-Boltzmann probability. It's an example of a probability law in high dimension, which, if you are at low temperature, has just two lamps. You can start with something simpler, like the Curie-Weiss model, for example. So, and I think this is interesting because first you can, and actually this is from where we started. So what I told you is before, it's a work done in collaboration with Marc Mézard, Tony Bonner, and Raphaël Urfin. But at the beginning with Marc, we started with on the Curie-Weiss model. Then, so it's also interesting because, as I told you, I mean, these diffusion models can be, one can think to use them to sample, to accelerate sampling. So understanding how they behave on statistical physics model is interesting. So in this case, well, what you can do is the Curie-Weiss. This has been done, as I told you, is by Marc Mézard and myself. You could try to do the one-dimensional Ising, for example. Again, exactly. But then I think there is an interesting, and this is more for mathematician, maybe. I think you can get some general result in case that you cannot solve exactly. So in all this case, you can do an exact analysis of the backward dynamics. But then you can say, OK, what about if I do it for the 3-dimensional Ising model? Will I see, again, regime 1 and regime 2, how the TS is going to scale? And I think, yeah, we can discuss later, but the answer is yes, there is a regime 1 and regime 2. But I think there is certainly space for a general mathematical analysis of model that you cannot solve exactly, but on which you can certainly give some exact results. Let's say, so general non-solvable model. And this is to be done. So, OK, let's say, for example, 3D Ising. And then, well, generalization that we did, and coming a little bit in the direction of what Gerard was asking, is, OK, now if you apply to real data, how we estimate where the speciation time is. So one way to do it is that what we did is that, I mean, the score, if you study the score, which is st of x, which is the gradient of log of pt of x, what you can do is you can do a large t expansion. So why we can do a large t expansion? Because, well, in all this equation, even if we have a more complicated problem, we know that at large time, the variable is almost a Gaussian with some correction. So we can do perturbation theory around this, and we can study actually how the score change in perturbation theory starting from large time. And if we do this, what we find is that the speciation time is equal to 1/2 of log of lambda, where lambda is the largest eigenvalue of the correlation matrix of the data. Correlation matrix of the data means just that you have xi, xj, which equal to, let's say, well, let's call it Cij. You take the eigenvalue of this matrix, you look at the largest eigenvalue, and indeed, if there is a class, there should be one big eigenvalues and then the other ones, and similar exactly to BBP. And so in this, you take the log, you take 1/2, and this should give you an estimate of where the speciation time is. Yeah.
So is there a dependence on D, a triple dependence on D of this lambda?
Yeah, so if you apply this to the Gaussian case or to the Curie-Weiss, then lambda scale like D. Then for real images, I mean, it's difficult to answer in the sense that, I mean, the image that you get has just that dimension. It's not that you can play with the dimension, so it's difficult to say. So you can see that indeed there is one eigenvalue which is larger, but now whether it's scaled with D or not for real images is not clear.
I mean, you can't just take patches of the images, or I guess.
I think you can try to do multi-resolution of the image, so increase artificially the dimension. Okay, we didn't try. I don't know. All right, yeah.
So you said that you start from something which has no overlap across the two. I guess the notion of no overlap, you could also formulate it in terms of the scale, right? Because you didn't give an explicit condition on sigma to mean no overlap, because if you take an arbitrary sigma, there will be an overlap, of course.
Yeah, I think so. Yeah.
So there's some condition on sigma such that there is no overlap, and it's linked to this condition you're stating here.
So well, I would say, so in the Gaussian case, the no overlap is just a condition on sigma because these are Gaussian variables. So now if you have a more complicated probability distribution, then let's say the non-overlap condition is, you cannot just relate it to sigma, but yeah.
In this case,
yeah, in this case, yes.
It's linked to this condition.
Yes, it's linked to, it's just one eigenvalue which is much larger than all the other, yeah.
But when you say that the effective dimension of the images is 20,
Yeah.
it means that basically you have a bunch of like 20 large eigenvalues, not just one huge one. You will have a bunch of large eigenvalues,
Yeah,
which will.
Yeah.
So
It's not exactly how they do it because I think it's more complicated because.
it's more complicated because it's not a Gaussian image. But let's say you have a Gaussian image like your example.
Yeah, then
this is
yes.
what you mean.
Yeah, then yes. But in real data, it would be true if the data it's a lower dimensional plane, then yes. But if, I mean, the thing is curved, which is curved, then you cannot get it from sigma. Okay, now I go back to the slides. Up. No. Okay, and I have. Should I do? Oh God. All right. Okay. So let's see now. Let's do numerics and see whether what we have derived with simple models hold or not. So this is an example of what we did, and then other people did later. So we took images, and we decided to take images in which artificially we just choose two classes. Of course, you can choose more, but since we want to compare to the computation that we did, so we just choose two classes. So here, well, I don't know if it was Panda Seashore. Here is 1 and 8. Well, are different kinds of images. This is male and female, conference and churches. So you see different sizes of images, different kinds of images. And we train, it's a state-of-the-art, at least at that time, model, not too big, but still you see 25 million parameters on this, on a number of data which is I mean, it can be very large, like 40,000 sample. And then, so the idea is that now we have the two classes in all these cases, and we are going to see whether, well, what we found makes sense or not.
So, but capital N was the dimension of this.
Yeah, this is 64 by 64. I mean, this I just squeezed 64 by 64 times 3 because there's the color.
So the dimension is 12,000, and you have 40,000 samples.
Yeah. Okay, so first thing, I mean, it's as I told you, the thought experiments in terms of cloning, you can do it in practice. So in practice, you have train your diffusion model, then you run the backward process at a certain time t. Well, you use two different thermal noise, so you have two different trajectory, and you ask whether you get the same image, the same class of image. Let's say if I have panda and seashore, do these two trajectory give both a panda or both a seashore or not? Okay, so you can test. It's easy to test whether they do it or not. And then, so what you have here is the probability that they end up in the same class as a function of t over ts, the same thing that I told you before. Ts is obtained like 1/2 of log of lambda, and these are, so I mean, lambda is different from the different data sets that I discuss. It changed quite a lot for some. But then, well, what you have here is that when you renormalize time with respect to this ts, you get a curve which is actually not too far. This is the example that I told you. So in the simple Gaussian mixture, depending on the dimension, this is the curve that you get as t over ts, and this is what you get here on real images. So what this is telling you is that, I mean, the effect is really there. So there is a certain time scale which, at least approximately, can be captured like 1/2 of log of lambda. And if you are in the backward process, you are before the trajectory didn't commit yet to a class. And if you are above this time scale, so at the end of the backward process, the trajectory have committed to a given class. Okay, that's good news.
Have you computed the second top eigenvalue?
So in this case,
because then it should probably give you about the. I mean, if you have really much larger, you should have something sharper.
If they are very well separated, or you mean, yep, no, you're right. Yeah, no, we didn't think to connect the how much is sharp with the second, but yeah, we can look at this. So there is a very nice, now we did it with two classes, then you can ask, okay, in real life, you have more classes, as I told you. I mean, you have different kinds of, so this, I mean, it's S is, we call it the speciation transition, but indeed it's, in real images, you have many classes. So for example, even with the example of cat and dogs, then you have different kinds of cats, then you have different color, even if you decide what is the species of the cat, and so on and so forth. So there is another way to see this transition, but now in a case in which you have many classes, is this U-turn experiments that has been first done by Cherkov and Bejo in 2023, and then repeated by many others. And this image is from this paper of the group of Mathieu Viard. So what they do here, so the U-turn is the following idea. So you start from an image, and you go forward, and at a certain time t, you go backward. So you go forward with, I mean, just with the Oyst and Uhlenbeck, you arrive at time t, and then you go backward using the score and a certain thermal noise. Now, you realize that, well, if you go very, very far in the forward process, if you start, I don't know, from a cat, and you go very, very far, if you just have cats and dogs, you go very, very far, you come back. When you come back, you can get whatever, either a cat or either a dog. If you just go a little bit and then you come back, well, if you start from a cat, you should get a cat. And so here is what they get when they train on image. I think it was just, I don't know whether it was generic images or images of animals. So they start from this, which I think it's a leopard, not so sure, but okay. So this is the initial image. Then they go a little bit farther, and then they come back. And what they get is something which is, as you see, is very similar, but actually, well, you don't see it maybe, but actually the color of the eyes has changed. So I think he has blue eyes now. And then if you go a little bit farther and then you come back, well, it's still a predator, but it's a wolf now. It's not a leopard anymore. And then if you go even farther and then you come back, well, actually, well, it's a butterfly. Okay? So you have this effect with multiple classes. All right, so other questions? So now what I would like to do in the remaining time is talking about conditional diffusion models, because typically when you use generation of images, you say, I want to see, this kind of image. I want a cat, I want a dog, I want an angry bird, and even with song or video. So I want to tell you a little bit about the story on conditional diffusion, also because it makes a nice connection. So I can tell you that this idea that comes from, let's say, statistical physics or probability, are useful to understand how this model works, but can also be used to improve the methods. Other questions before? Yeah.
Sorry, in the U-turn experiments, do you basically see the same phenomenon, like the kind of, it's really, in some small region, for most of the time you run it forward and you can do this for a long time, and then you can run back and get the right rough animal, so to speak, or if there's 100 classes, you still have the same class, and it's only like right at the end where you differentiate, like is there some transition here similar to the two?
Sorry, no, I think I didn't understand the question. So you say in the U-turn?
Yeah, so like with only 2 classes, there's some like timescale regime 1 that's like shorter, if I understand correctly, than that.
Yeah, so this it means that when you're in different classes, actually there are multiple transition in a sense, or multiple crossover. So first you decide, I don't know, let's say whether you get a predator or not, and then what kind of predator, and so on and so forth.
Yeah, but in this picture, if I understand correctly, like what is the relative scale regime 1 to regime 2 just in the 2 classes? Like should I think of 1 as much larger time scale than the other? Or?
Yeah.
So the 2 is much larger than 1? Right.
So you're going backward, but it depends. If you're going forward, regime 1 will arrive at the end, whereas if you're going backward, regime 1 it's at the beginning, and then you have to go to much larger time to start to create the property of the images.
Yes, is that still the case here?
Yeah.
What I'm asking.
Yeah.
Okay, so
yeah, because here you see, you are going forward, so what I'm saying is, if you go like this and you come back, you don't change really the class. If you go here and you come back, then you change class. And the example here is just that you have multiple classes. So what happens is I go here and then I get a different leopard. I go here and come back, I get a wolf. And I go here and I come back, I get a butterfly.
Yeah, but you're really going like very far. Like much farther each time.
Yes, exactly. Yeah.
Okay.
Yeah. Okay, so now conditional diffusion. So conditional diffusion, in principle, there is nothing mysterious and nothing difficult. It's just that what you have to think is that the probability P0 of x, you can divide it in classes. So you have a certain fraction of data which is in given class C, and then you have a conditional probability, is the probability of x given the class. Okay? And the idea is always that if I give you a typical x, so we are in high dimension, and if I give a typical x, you can tell me what the class is. Because if you cannot, then it means that, it's not a class. You cannot really separate the system in classes. So there is, behind there is this idea that you are at least in larger dimension, and there is a concentration property which makes the probabilities divided in different lumps. And what you want, if you want to generate a data which belongs to a given class, well, what you have to learn is just the grad of the log of the probability of x conditioned to C. There is nothing more complicated than that. So what you should do is you just, if you say, I don't know, a bee on a flower, well, then what you have to take is the C, which corresponds to a bee on a flower. Okay, don't ask me how, but there is some black magic behind this. But you have just to compute, to use this score, and when you do the backward process, these are different examples that you get of starting from this initial condition and using different thermal noise. Now, yeah.
Classes here? In a very simple example like this, bee on the flower.
Yeah.
What is the collection of classes? Depending on what you choose, this whole thing will be completely different.
Yeah.
What is C?
Well, it means that you have a lot of data. So typically here, I think you have a lot of figure with a lot of captions, and these captions are transformed in some latent space to connect to some real variable. And then this real variable are the classes which correspond to this formal thing.
Captions are a bee on a flower.
Exactly, yeah. Okay, so what happens is that if you do this, you get these kind of things. And these kind of things, people in the, real practitioner then don't like that. They say it's not good. So what we are going to do, we are going to do something else. which is the following, which is what is called classifier free guidance, CFG. So what you do is that instead of using the force field, what you should do, which is this one, you use this force field, which is S x of c plus omega, which is some constant, which is you are going to adjust, let's say, of order 1, times the difference of S xc minus S of x. S of x is just the score, the unconditional score. Now, when you see this, it's quite astonishing, because there is a nice theoretical mathematical theory behind that tells you that you have to use this, and they say, no, 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 we are going to use this, which in principle shouldn't give you the correct target distribution. And indeed, if you do a simple example, you take mixture of Gaussian, dimension 1, then again you use, either you do it with the correct score, or you do it with this classifier free guidance score. And what you see is that, so here you have 2 Gaussian, and I'm just focusing, so this is a numerical experiment in 2 dimensions, and I'm focusing on just the all the trajectory that went to the Gaussian, let's say, on the right. And so what you get here is that, okay, this sigma hat, I think it's actually it's omega, but what you see is that actually, I mean, what you should get, I think is the yellow. And what you get typically, if you use the classifier free guidance, is this thing. So it's wrong. And then it actually, if you see what it does, so here is the Q of t. Q of t is like x1, the same thing that we discussed before. So it's the direction, is the component along the direction in which you have the Gaussian. So what you get is that for omega equal to 0, this starts to go in the backward. So this is the backward process. This is the trajectory. And if you put omega large, well, the trajectory is not following this. It's not as it should, but it gives you something else. So, I mean, that's kind of mystery. So you don't do what you should do. But what they tell you is that, yeah, you don't do what you should do, but these images actually are nicer than these images. Okay, so which, well, it's true. It's true that, I mean, the bees looks more like bees, and things are more sharp, maybe a little bit too much. And so actually, in all actually conditional diffusion models, this is what is used, and not this, which should be what math say you should do. So now the question is, okay.
For math to look at it.
So the question is, okay, why, how is it possible? And so, well, we started to think about this, and actually, this is a nice example, I think, to understand that if you think that there are different dynamical regimes and that you have high dimension, actually you can understand why this is not crazy. And so why this is not crazy? Well, the reason is the following. So remember again, so this is just a kind of illustration of, you go from 1 Gaussian to 2 Gaussian, you have regime 1 and regime 2. So this is just a projection for high dimension. And then, well, if you remember what I told you, in regime 1, I mean, you choose what is the class. And then in regime 2, you have chosen the class and you never change, okay? And so what happens is that if you look at this, I mean, this term here, which is the difference between the conditional score and the true score and the non-unconditional score, actually this difference is 0 in regime 2. You see why? Because in regime 2, if I take along a typical x, along a typical trajectory, in regime 2, so x, I mean, has chosen what is the class. So the conditional probability is just equal to the probability. And so the conditional score is just equal to the score. So in regime 2, well, this has no effect. This drops away. So this actually has just an effect in regime 1. And in regime 1 is not where you construct the image. It's just where you choose in which class you go. So what the effect of this system, of this classifier-free guidance is doing is, in a certain sense, it's pushing you. It's giving you a kick, a stronger kick to go in the correct direction. So if you choose to go to the class +1, it gives you a bigger kick to go to +1. But then actually the construction of the image which correspond to class 1 arrive in regime 2, and in regime 2 actually this has no effect. So it just push you, and you can check this. You take the Gaussian mixture, now you go in 200 dimension, and you see that actually the target distribution, which is now I'm focusing again on just on 1 Gaussian, is correctly reproduced. And again, so what you have is, if you look at the Q, so this coordinate x1, what you get is that the x1, indeed, you push strongly if the omega is the strength of this classifier-free guidance, it pushes you strongly in the correct direction. But then actually, after the speciation time, you go back to the usual generation. Yeah.
So if you use the same database and the same noise, and you have one thing that is classifier-free guidance, and the other thing that is the usual score, and that you pushes the, for example, the discretization in time of the usual score further, would you obtain the same?
What do you mean the discretization time?
I don't know, like, would you expect the output to be more or less the same if you...
Well, if you use the same data and the same noise, this is this is really this is obtained with the same data and using exactly the same initial condition and the same thermal noise.
True, okay. But with a U-turn, for example, you should be able to, or maybe I missed something, but with a U-turn, you should obtain the same using classifier-free guidance or the usual score, right?
If you don't do the U-turn too long. Yeah, I think so. Yeah. Okay, so this is just to tell you that, so this actually explains that the existence of different dynamical regimes and the fact that you are in high dimension, which makes that the different regimes are there, actually explain a little bit this mystery, at least a part of this mystery, is why actually you don't do the correct thing that you should do, but still you get something which is correct, which makes sense. Now, there is a part of the mystery that is still not answered, which is actually why it's good to do it. So we are saying that it is not wrong, it's not going to give you a wrong result, but what they do in practice, they tell you that it's better to do this. And the idea, but nobody had, for the moment, did any real theoretical studies, is the estimation. So behind all this, I never discuss how you learn the score. And now the idea is that when you push the system toward the correct class, you push the system in a part of configuration space in which actually the score is learned better. And this is our idea, at least, why it's useful. So you push it there where it's better learned, and once you are there, then you create the image. And then, given that we have understood that in regime 2, these things go to 0, and so the only effect is to push in the correct direction in regime 1, then you can say, okay, why just doing something linear? Here I can put a nonlinear function, which is a function of the difference between the absolute value of the two scores. And I can play with it. I can push stronger if I want, or I can push maybe not as much at the beginning of regime 1, but a lot at the end of regime 1. And so this is just something that we did. So this creates some nonlinear version of classifier-free guidance with a parameter alpha that has to be larger than -1, but besides this, it's just a parameter that you can use. And if you do it, this is actually a work in collaboration with Meta. And if you do it, actually you get images. This is the same example, same number of data, and same thermal noise, same initial condition. This is what you get compared to this one. And if you use, I don't know whether with your eyes you could say that this is better than this, but it's true it's more diverse. And then if you use some quality that they use in computer science to get the quality of the image, actually these images are better than this one. So it doesn't prove that we have understood everything, but it just gives you, I think it's a nice, so we started to ask theoretical ideas based on things that come from, let's say, engineering and computer science, but then, understanding things about theoretical, things about the existence of dynamical regime, then we can actually then try to improve also some algorithms that are used in realistic application. And with this, I think I will stop here, and tomorrow we are going to discuss memorization versus generalization. Thank you.
Thank you very much. Are there any questions?
Just to check that I understand this, what you said in general, the speciation time is given by log of large size log.
Yes.
Is this like a quantification of how close two images are, like two classes of images, how much we yeah,
I think so. Yeah, it's related to how much the two images. So what you have to do is you have to know what is how distant are the two classes, and then you want you know that you are going to put noise on the image, and then the speciation time is the time at which you blur so much with the noise that actually the two things which were separated, they just become a big potato. So yes, so it's a measure of the distance between. Yeah.
So the picture you gave us is that there's some number of classes, each of them has a speciation time, and there are like dynamical transitions at each time.
Yeah.
But I imagine like if you had somehow like a really large data set that's like super high resolution images, then actually you might have an almost infinite hierarchy of classes with speciation times that might kind of like densely fill your time axis. And so really there, a continuum would be a better descriptor. I'm wondering if there's like, so you give us like a Gaussian model that has one speciation time. Can you design a model that has infinitely many speciation times?
So formally, yes, you can do it. Now in practice, as you said, I mean, D is finite. So I think there are a certain number of classes in which you can really understand, I mean, show that there is a crossover. And then at a certain point, there is no real sharp crossover that you can define. And also at a certain time, you enter also in the regime in which I was saying, the lambda I. So it means there is in images, there is classes, but then there is also the fact that you have, I don't know, microscopic property like edges and things like this. And this will be recreated at a certain time. So if the time at which you recreate this microscopic property is mixed up with the time on which you would like to have speciation on different classes, then you cannot resolve them anymore. So this is kind of theoretical image that can work if the classes are very well defined, but then things are blurred at a certain point. If you want to do a theoretical model in which in which D go to infinity, you take Gaussian mixture, which are all separated of order D, but with different, I mean, or separated by D with some power, with different power depending, then you can construct it, I think. But then in reality, since this is finite, at a certain point it's blurred.
Do you mind going back one slide with the output, the nonlinear CFGs? So it seems that the flowers, like the background, is actually worse compared to the top, right? So the bumblebee looks nicer, but the flowers maybe lose some.
You're right.
But is there a way to sort of?
I mean, I have to say that. I mean, it's not that. I wouldn't bet, and I mean, it's. I know that they have this quality factor, and on which for them it's really important. If you beat someone on this quality factor, then you are.
But a botanist or a horticulturist will say the flowers look messier.
Yeah, I agree. I mean, to me, the interesting thing is more that I mean we can go. I mean, this linear guidance. Once you understand what it's doing, then you can actually make it more general. I wouldn't. I mean, it's. I agree. Yeah, the flower, and also actually when I say a bee on a flower, actually I have to say that I don't know what is the prompt that actually my student Kruno used to create the image. So I put it just like that. I didn't ask him. I should have asked him what was the prompt. So I'm sorry. I lied to you.
So in the multiple classes case, so you will see the same phase transition in the effective potential, right?
Yeah, you will see.
With just a potential with multiple wells, or would it be more structured with like clustering of minima or something like that?
So you would have like, I think it's, so for example, if you have 4 classes, like the one that I described with 2 Gaussian here and 2 Gaussian here, so now the potential that you have to consider is 2-dimensional, and so it will form, I think, okay, let me write maybe, so if you have the case in which the Gaussian are, one is here, one is here, one is here, and one is here. So what you are going to get you will get a 2-dimensional, so at the beginning the potential is just like this, just one big well. Then we'll start to have 2 wells here, and then these 2 wells will separate in 4 wells like this.
So in the real case you would have presumably more than 4, right?
Yeah.
Number.
Yeah.
And if the same thing happens for all of them in that.
But yeah, I mean, in the real case, we don't know how to, I mean, we should think about, but we never thought whether we can really see a potential and study the potential, because it would mean that, yeah, well, you know exactly what are the direction. I don't know, I have to think about. We didn't think whether it's possible to plot this potential for a realistic case.
Okay, well, if there's no more question, well, thank you
you
again.